Okay. Okay, well, welcome everybody. Unfortunately, the problem with my iPad has still not been fixed. I contacted Zoom and they said they'd be uploading a new version of Zoom today, but not yet. Apparently, it's stuck somewhere in Apple's Apple approval process, but hopefully by next class. So today I'm going to use. I won't be able to write so well on the notes, but I have a blackboard, a whiteboard that you can see. That's a separate window, and occasionally I'll go walk over to the whiteboard and write things on that. All right, so let me share the file on vortices. So hopefully you can all see this. All right, so any questions on vortices that we discussed last time, which we're going to continue today? Okay, so let me just quickly review then. We start with the Ginzburg-Landau free energy of a superfluid. We're just looking at static configurations here, so there's no time evolution. And we also simplify and make everything independent of the z direction. So it's a matter of minimizing this free energy with a two-dimensional complex field psi. Of course, the global minimum is psi equals square root of minus alpha over beta. But we impose a condition that the phase of psi has a winding out at infinity of n, where n is some integer. It has to be an integer, otherwise psi is not single value. Okay, so you insert this in here, and this is what the free energy becomes in terms of the radial function f of r. And then we showed that as r goes to 0, f should go linearly with r to the power n, or mod n, sorry. That's the optimal configuration. And this implies that the current, which is obtained by taking the derivative of the free energy with respect to the vector potential, and of course we add the vector potential as we will in a minute, just as a covariant gradient. That also brings down a factor of 2e over h bar c. Unfortunately, I didn't put that in here. I'll fix that. And so then you find a current of the bosons or Cooper pairs, which is pointed in the angular direction in this vortex configuration. And at large r, the current goes as 1 over r, so it decays to 0 at infinity. But it also decays as r goes to 0, because f of r vanishes as r goes to 0. So here's kind of the picture. There's a region we call the core of the vortex, where the function f, or the amplitude of this order parameter, goes to 0. For n equals 1 vortex, it will just go linearly to 0. N equals 2, it goes r squared, and so on. And then it approaches at infinity the equilibrium value of the superconducting order parameter. So the supercurrent is 0 down here in the core of the vortex, and also at infinity, and there's a region around which it's flowing. And the circulation of this current, or if you interpret it as superfluid helium 3, the circulation is quantized. We're going to think about charged vortices most of our discussion. All right, so then the next step is to take this f of r, which we have found minimizes the energy subject to the presence of a vortex, and plug it back into the free energy and see what happens. And it turns out, okay, so then there's two regions, roughly speaking. There's the core region where, it's going to be some finite number, but there's the far region, and we do have to worry about the far region. That's where the most interesting things happen now. So in the far region, f is not quite, not equal to the value. It only goes to, approaches its, sorry, no, F is approximately square root of alpha over beta, but theta there's still some appreciable theta dependence over here. So if I look at this free energy, if I go R very far away, let's see, I hope I'm getting this right. Yeah. So these terms here, this approaches the equilibrium value. This also will fall off very fast, but there's this term right here. If you look at this term, n is a constant, f goes to a constant. It falls off only as 1 over r squared. So that's, however, that means that the energy was going to get a contribution that's divergent at large r, because if you pick out this term, when n is non-zero, so if you now evaluate f vortex minus f no vortex, there's a contribution from that term that doesn't quite vanish. In fact, it is not even finite. So this goes to 1 over r squared. You integrate this, you get integral from the core of the vortex to infinity of dr over r, and that's divergent. So this is saying that if you just had a single straight, perfectly straight vortex in a superfluid, actually you're never going to get it in equilibrium because it costs an infinite energy per unit length. And it goes as log of the system size. That's really infinity has to be cut off. Okay, log of the system size is not that large, but still it's infinite the larger the system becomes. Okay, and that's in fact correct. So isolated vortices are prohibited. However, what you end up having are vortex anti-vortex pairs. You have two of them, just like like a dipole. And then when you try to evaluate the energy of the dipole, well, we're not quite sure exactly what it will be, but we have a guess that as far as the log is concerned, instead of going to infinity, roughly speaking, as far as the log is concerned, you only have to cut off that integral at the spacing between the vortices, because once if you get vortex anti-vortex pair, if you go far enough away from a vortex anti-vortex pair, it looks like no vortex because there's no net circulation. So there's no contribution out at infinity. That falls off as 1 over r squared. So you expect the log to be cut off at roughly the spacing between the vortices. So this then has a finite energy. Okay. So when we consider the costless Thouless transition, which we will in a while, this log will be crucial. So the energy of the vortices goes roughly as a log of the spacing between them. And then you also find in a two-dimensional film anyway, that the entropy of this also goes as log of the spacing between them. And so there's a balance, and there's in fact a phase transition. In one region where the entropy wins, the other region where the energy wins at some critical temperature, and that's the famous costless Thouless transition. But we'll come to that in much detail as probably in a few weeks. Okay, any questions on that? So that is the all correct answers for a neutral superfluid. A perfectly straight vortex has some energy per unit length, which diverges logarithmically with the size of the system. And a pair of vortices has an attractive force. The energy goes as log of r, which means the force between a vortex and an anti-vortex goes as 1 over r, the derivative of this. For those of you who know these things, the 1 over r is the form of the Coulomb force in 2 dimensions. In 3 dimensions, 1 over r squared, as you know. Okay. So there's an analogy between the vortex anti-vortex gas in 2 dimensions and a Coulomb gas, which we're going to exploit in the theory of the costless Thouless transition. Any questions? Okay, so now let's look at the same question, but for a charged scalar, which would be the appropriate for a superconductor, for electrons. There is a gauge field. So if you have a supercurrent of Cooper pairs flowing around a vortex, that current is going to produce some magnetic fields by Maxwell's equations. This is like a solenoid of current flowing this way. So you'd expect a field produced by this out of the plane. And so we want to think about what is that magnetic field that's created by the supercurrent when you have a charged condensate. All right, so now it turns out, quite amazingly, once you put the coupling to the electromagnetic field, the energy of the vortex is no longer divergent, it becomes finite. And so these vortices can occur on their own in thermal fluctuations because of there's a beautiful cancellation that occurs far away. Roughly, the idea is that, once you have a charged scalar field, this phase, this phase theta is not even gauge invariant. It's really a gauge artifact. So as we'll see, the vector potential can arrange itself in a way to get rid of this divergent energy at large R. Okay, so we're going to try to do the same thing here in the presence of a vector potential. So we make an ansatz that psi is some f of r times e to the I n theta. And it turns out the basic point you can already see by going to r, it goes to infinity. So let's even forget, just go to very large R and just assume at large R, there's some winding in psi. Okay. So what we're going to try, so that costs some energy normally because of the grad psi term. Grad psi squared will act on this theta and give you this 1 over r squared energy, which diverges. So we want to cancel that out. And so we're going to basically cancel grad psi with A times psi. And amazingly, it turns out you can do that. So like I said, if you have these currents flowing, what you expect is some magnetic field near the core of the vortex coming out of the plane of the screen or into the screen, depending on the right-hand row. But you don't expect, so there's some net magnetic field in this region, but we're going to try to arrange things that there's no field outside, really far away. We don't want to create too much field. That itself will cost energy from the vacuum Maxwell term. So we just want a field in this region. So there's some net flux in this region. And when we go far out, we want there to be zero field. Okay. At the same time, and this is, of course, the beautiful thing about quantum mechanics, zero field does not imply zero vector potential. So we can use that trick to cancel between these two terms by taking a vector potential that's non-zero, even though the magnetic field B is zero. Okay. So what we're going to assume is that the vector potential A also has some associated with that is some coefficient phi, which we'll see in a minute is just the flux over 2 pi r times e to the e theta. Okay, now you just look up the formula for the curl for this particular vector potential that falls off as 1 over r and points in the theta direction. That's just zero. Okay. However, that doesn't mean the field is zero everywhere, because the field over all space, d2rp, by Stokes' theorem is a line integral of a dot dl on some curve that is very far from the core of the vortex. So we're taking some curve out here. So let's see if I can annotate this thing. Draw. So we're taking some big curve out here. This is our curve. And then we do that integral on that curve. Okay, how do you get rid of this silly thing? Eraser. Yeah, you take that integral on that big curve, and you do it for this. Just take that integral using this form, and that's just phi. So the dl gives you 2 pi r, which is why I put the 2 pi r over there. So basically, this phi is the flux, the net flux near the center of the vortex, which this vector potential is associated with. So there's no field far out, but there's some flux in some region near the vortex. And it could be zero when we optimize the energy, but let's see, we're going to use this fact to our advantage. All right, so now we just plug this in here and just look at the gradient term at large R. Okay, so that's quite easy. So you just take this. We're only interested in the divergent contribution. So we just take this and then take the radial integral grad of psi will give you a factor of n times r in the theta direction. And this is already pointing in the theta direction. And so you see, you just get this number, n minus q phi over 2 pi h bar c times 1 over r squared. So if you pick an arbitrary flux phi for any given vortex with vorticity n, there's still a divergent term. It's just this is the coefficient of the log r term. Okay, but now you notice you can, I haven't told you what phi is. So if you want to minimize the energy, surely you want this thing to be 0. So the actual saddle point, you want this to be 0, meaning phi is n times 2 pi h bar, which is also known as h, c over q. And then there's no more log divergent, and the whole thing is just some finite energy. So we see that the flux of a vortex is n, which is the vorticity, times phi naught. And phi naught has the units of flux. It's called the flux quantum. And it's just given by fundamental constants of nature. It's just given by Planck's constant in CGS units, velocity of light divided by the charge. If you use MKS units, it's just there's no C, it's H divided by 2E for a superconductor. So you can have a vortex in a superconductor, but this elementary vortex, of course, would be n equals 1 or minus 1. And this vortex has a quantized flux of H over 2E. Of course, this was first discovered by Abrikosov. And now it's routine to see these things in STM experiments. They actually exist. You get a whole lattice of them when you put a magnetic field on what's called a type 2 superconductor. I won't go into the difference between type 2 and type 1. In type 1, basically, the system goes normal rather than allowing for vortices when you put a magnetic field on them. But yeah, and this was the prediction. This was a prediction of theory. So this was, quite amazing. People were just working out this theory after the independent of the BCS theory, really, in Russia, the former Soviet Union. From this Landau-Ginzburg theory, Abrikosov predicted a whole new phase of matter and a whole new type of vortex with quantized flux, which is, of course, now routinely observed and was soon after seen in experiments. Although he eventually won the Nobel Prize for this prediction, but many, many years later. I forget when, but I think in the 21st century, maybe even. The prediction goes back to the 60s. Yes, question.
So could you say more about how these are detected in experiments? Like if we impose some magnetic flux on the system, how does it get quantized?
Yeah, okay, that's a great question. Let me, for now, let's just figure out what is the end. Let me just show you what the magnetic field actually looks like, and then I'll return to that in a minute.
Okay, thank you.
All right. So, but yeah, okay. So this, this seems like a rather special argument written for polar coordinates in a system that has no disorder and cylindrical symmetry, but it's really much more general than that. It's a very, very general argument. Even if you have disorder and a sample with no cylindrical symmetry, this basically follows quite easily. So basically, you assume you have some defect, some vortex, and as R goes to infinity, there's some configuration where psi, the amplitude doesn't vary, but only the phase varies. So if we just plug this into this, that's equal to precisely that. And now you want this to cancel that. You want A is pure gauge, and therefore it can be canceled by grad theta. So this must equal that. And then the line integral of the left-hand side, normally it's 0, because of the gradient of some function. But if theta has a non-trivial winding, this line integral is 2 pi n. That's the vorticity. And this is just the flux. So there you go. So that's the very simple argument. You can quickly just see without any additional assumption that this is indeed the flux quantum. All right, so now let's figure out, so how do we do that? What is the function of A of R? Well, okay, so now let's imagine, there are no external sources right now, but somehow there's some thermal fluctuations. So what is the free energy we have to consider? Well, the free energy is the Landau-Ginzburg free energy F. But I also have to add this vacuum Maxwell term, 1 over 8 pi b squared. That's the energy density of the magnetic field. So when you, if you take the variation derivative of this, it gives you Ampere's law and so on. But when you create a magnetic field, you have to pay some energy cost for that. All right. So the fact that you were able to get, but you're willing to do that, you're creating the magnetic field only in the core. And so you're willing to do that because it gains you an infinite amount of energy far away, which is this divergent term. But so there is still, the core, however, will cost more because of this term. Okay, so this is your free energy. And now you have two fields. You have psi and you have A. And you have to minimize with respect to both, subject to the condition of a non-zero flux or equivalently a non-zero vorticity. They, of course, have to be related to each other. So you have to solve these equations, these Euler-Lagrange equations. This will, of course, give you some version of Maxwell's equations. Curl B is the supercurrent, and this will minimize psi in the presence of an A. All right, so that gives you a complicated set of equations on which books have been written, and I won't go through the solution. Let me just qualitatively show you what happens. What happens is that this vortex core for f of r is pretty much the same as before, about the same distance psi sub c. Psi sub c was square root of minus alpha over beta. Oh, no, sorry, I didn't mention what psi sub c was. Oh, this psi, yeah, here it is, square root of alpha over gamma. So I should have mentioned that. That's the size of the core. So it becomes bigger and bigger as alpha goes to 0 near the critical point. More and more of the, so but the better the superconductor, the smaller the core. So the superconducting order parameter vanishes in about the same way. And the magnetic field, there's some flux which goes to 0 eventually. And what is this scale? Well, that turns out, you won't be surprised to learn, is another length scale we met before. It's the London penetration depth for a uniform field. So basically what happens is when you have a vortex, and in a type 2 superconductor, the psi c is much smaller than lambda L. So when you have vortex, you have the superconducting core in the center, and then out there's for a while in the core, the field B field is basically uniform, but eventually it'll go down to 0. And so that's about the point where B goes to 0, where this log divergence is cut off. So, but this is a finite length, and so this tells you that the log divergence will now be log of the London penetration depth, not the system size as it was before, divided by the coherence length. Okay, so there is a finite energy cost to create this, and you've got, which the larger the London penetration depth, this will be larger. So now the question was, well, okay, this energy cost actually in a real superconductor is prohibitive. It's not going to do it on its own, or you won't, even if it does it at such short scales near TC that you're not going to be able to see them. So you have to make this vortex configuration the global minimum. And how you do that is, well, you have to apply a magnetic field on your own. Okay, so here's, now you can switch. Let me stop sharing. I'll draw this on the other me with the whiteboard, and I show you what we're talking about here. Okay, so we said that the free energy of the system itself was, well, there was a free energy of Landau-Ginzburg, and then there was 1 over 8 pi del cross A squared. But then you have a magnet which produces its own magnetic field. So external current. There's an external current here, Jx, and then this will, couple to the vector potential. Let's see. Oh gosh, I should remember it. Okay. Well, I don't know. I think it's, what is the coupling here? Is del cross B or something like that? J. Oh, I'm sorry. I should have looked this up. Okay, I've forgotten that. Okay, there's some coupling to external current. Let me fudge a little bit. Plus coupling. No, okay, I think I know what it is. Yeah, so yeah, the way to write it is the following. Okay. So when you bring it in a magnet. So what the magnet does, this is some Bx. It wants del cross A to be equal to B. Yeah, that's the correct expression. All right. So what's going to happen? Well, here you have a sample sitting here. That's a little thin slab. And then you put some Bx from some other from some other currents. And here's your superconducting sample. So well, now when this is a normal metal, well, there's some magnetic permeability that you learn in E&M, but mostly speaking, this phi field will just go right through. Nothing much will happen through the sample. So this is for a metal. Okay, but now imagine if you lower the temperature, and this becomes a superconductor. Okay, but what's going to happen now? Well, what happens now is you get, and I apologize for my artwork here. This uniform B field will split. So let's take the limit where the B field is fairly weak. Then you're going to get these vortices, okay, which will form in general a lattice called the Average-Kosov flux lattice, and it's usually triangular. And what will happen to the B field was that initially the flux line were uniform. What's going to happen is that the flux lines will kind of all go in a region of order the London penetration depth near the core of the vortex. The London penetration depth is a bit larger than the supercurrents themselves. But anyway, so the B field will split into, well, okay. It's going to granularize itself. So if I look at it from the top, there'll be regions here where B is non-zero. So this is B not equal to 0. And there'll be regions here where B is basically 0. So there'll be supercurrents, and the B field will become highly inhomogeneous and be associated with each vortex. And of course, in the end, to make sure this works out right, the density of vortices will be adjusted by external field, so that, roughly speaking, what's happened is that the external field, which is some uniform field, it'll split into flux quanta. Each little lump here will carry one flux quantum, and the number of these vortices will be just right, so that the density of these vortices multiplied by the flux quantum gives you the external field. Okay. So, and you can then take your STM tip or do some nanoscale mesoscopic measurements of magnetic field and see this lattice. Okay, so I hope that answered your question, Patrick. Any other questions? So that board kind of works? Yeah, I think so. You have to go to speaker view and click on it. Then you can see it, yeah. Okay.
So,
Yeah.
so from this analysis like that we've done so far, can we extract some sort of like critical temperature for type 2 superconductors?
Well, I mean, let's see. There's an HC1 and an HC2 as a function of field. I mean, the temperature dependence right now is kind of trivial. It's all in the values of alpha and beta. So this is just a minimization of the free energy. All they're doing is normalizing the value of alpha and beta, the coupling constants in the Landau-Ginzburg free energy. A separate problem is to do thermal fluxion of vortices themselves. I mean, the vortices will also move around at finite temperature, but that usually is much weaker effect. That only very thin films near the causeless solid transition do we have to worry about that. But at low temperature in a bulk superconductor, the vortices are such big objects, they're mesoscopic scale, that there's essentially no thermal fluctuation in their position. Patrick, you had another question?
Yeah, thank you. So that what you explained makes sense. I think I'm still wondering what happens in a situation where the external field is only applied in like a local region, and the external field isn't an integer number times a flux quantum.
Oh, okay.
Well,
well, you're asking what's going to happen on the edges. I think that's the kind of thing that's difficult to say in general. You have to solve these equations, but in the end, you just have to minimize the expression that's on the whiteboard, that whole thing, for whatever your geometry is. Yeah, it could have a more complicated solution. Yeah, the vortex lattice solution, of course, is assuming an infinite sample, and of course the vortices can move around. They can get stuck to the edges, and then all kinds of other things could happen. Yeah, the flux quantization argument really assumes that there's a large region outside a vortex where you just got a perfect superconductor. Okay, it really, there's for this thing to diverge, I really need a lot of R going all the way, much larger than C. But if you have a finite sample, that integral is not finite, and the flux need not be quantized either. Yeah.
So in the event where there is a huge superconducting sample, but what if if you have a huge superconducting sample but only apply magnetic flux in a small subset of it, but that magnetic flux isn't an integer times the flux quantum?
Yeah, so at least within that region, you'll get the right density, but there'll be a little bit left over. And what happens right at the edge will be something very complicated. I don't know in general.
Oh, I see. But you get something. I see.
The vortices kind of start to break apart near the edge in some way. And the flux is no longer quantized because near the edge, you don't have a large region for this energy cost to really matter. Yeah.
Let's see. Okay. Thank you.
I mean, this quantization only makes sense. Well, yeah, okay. For a single vortex, you don't need a very large region for this to work. There's another for a perfectly periodic structure, infinite periodic structure. Again, there's a quantization from a slightly different argument. It has to be quantized for a perfectly periodic structure, even without any infinite regions. But once you don't have something perfectly periodic, and you don't have these very large regions separating the vortices, then there's no reason for quantization.
Okay, thank you.
Yeah.
So when the magnetic field gets very large, what happens? Does the superconductor break down in some way?
Yes, eventually when the vortices start overlapping, that's called the upper critical field HC2, and then the psi just goes to zero, and you get a metal.
I see.
So eventually in a strong enough field, you'll lose the superconductivity, the Cooper pairs will disappear, and the magnetic field will just penetrate the sample.
Gotcha. Thank you.
Sure. Okay. I think we're done with this chapter then. All right. So that's pretty much what I want to say about superconductivity and superfluidity in the sense of, theories from the 60s and 70s. I've kind of chosen to review material that we're going to need in our discussion of more modern phases. And in fact, I realize your problem set on superfluidity is not due till September 30th, was it? But I'm in the next couple of days going to put another problem set on. Won't be due for several weeks after that on BCS theory. It'd be good if you can get to work on it now while the BCS theory is still sort of fresh in your mind on some simple problems on superconductivity. Anyway, so any further questions on superfluidity and superconductivity in general before we go to the next chapter?
Sorry.
Yeah, go ahead.
I have a question about this picture. So would the field on one side and the other side of the superconductor look different? And if so, how do you decide which side looks which way?
You're talking about the vertical direction in this?
Yeah.
Z direction? It'll look the same, roughly. I mean,
okay, so
of course, when you're far enough away, of course, it's going to depend on where your current source is and all of that. This is, I'm assuming there's a current source out at infinity that produces the Bx, and the Bx will now, it'll basically lump up in the superconductor and then spread out again in a symmetrical way.
Oh, okay. Thank you.
Yeah. So it becomes, the magnetic field becomes kind of grainy on the scale of the London penetration depth, and then becomes uniform again. So,
Subir, can you explain more about what you write on the whiteboard, the cross A minus, the curl A minus B external?
Yes. Okay, sorry. So, so this is just the free energy of everything. So of course, if you just have a superconductor sitting on its own, I think, let me see, yeah, you can see me, right? So if you have a superconductor sitting on its own, then your free energy is just this, okay? This is what Maxwell told you. This is the Maxwell vacuum energy, and this is the Landau-Ginzburg energy. But now I have another current source, which, I have some magnet, I have a power generator, and I'm producing current somewhere else in my lab, and that's producing a magnetic field. And that magnetic field, if the superconductor wasn't there, that magnetic field would have the value Bx. So I just account for the current source, the energy of the current source, by just saying, okay, the value, if I didn't have a superconductor, then del cross A would be just Bx, and that would minimize the energy. So this, if you take the variations of this, you'll just get Maxwell's equations, basically, where the magnetic field, physical magnetic field A is created by the external current. So there's some external current, and del cross Bx is equal to 4 pi over C Jx. Yeah, this is how you think about it. So you have some Jx that's in your lab that you have on some control. And from that Jx, you'll get a Bx. And I'm just going to say, okay, if I plug this in here and take the d by dA of this, I'll just get Maxwell's equations that del cross A will be 4 pi over C Jx. We can check that. Okay, so now I have those currents, and I'm going to assume those are just given to me. They're not going to vary. There's no feedback. They're just so large that they don't care whether a tiny little superconductor comes by. So that's fixed. This is something given to you, some constant. But now you want to figure out the actual magnetic field. Well, the actual magnetic field will have two contributions. It will have one contribution from the external source, but it will also have a contribution from the supercurrents that are going to be created here. So I want to figure out the physical magnetic field, the full B, the physical, the actual, there's only one physical field, That's del cross A. I want to figure that out. And the actual Maxwell's equation is del cross A is 4 pi over C Jx plus J superfluid as both such terms. So where do I get this equation? Well, if you just take dF by dA equals 0, that will give you this equation. So where will you get this term? You'll get that from there. And where you get this term, you'll get it from here. Okay. And you can check, you just work it out. This will all work out correctly. So this is just a quick, so minimizing the free energy is just another way of figuring out what are Maxwell's equations. You're combining Maxwell's equations to determine A and B to determining psi, which is the Landau-Ginzburg order parameter. Okay. So what's happening here is, normally if you're when you're doing E&M, somebody says, oh, here are my currents determine the magnetic field. Well, here I have a more complicated problem. I tell you there's some external currents, but I don't tell you what are the supercurrents. I don't know what they are. So I have to solve both problems at the same time. I have to determine the supercurrent, and then I have to determine from that supercurrent and the external current the total field. And those two problems I can solve by just solving these two equations. This total F, dF d psi equals 0, and dF dA equals 0. So this gives me Maxwell's equations, the full, and this gives me the Landau-Ginzburg equations, and everything is just equivalent to minimizing this free energy. Okay.
I see. Thanks.
So now you see, that's why it's so much nicer to think of free energies and all Lagrange's equations. All these things become really very simple. There's always just the same set of equations. You just find the right independent and dependent variables, right on the free energy, and then minimize it.
Subir?
Yeah.
So the vortex core size, the psi sub c,
Yeah.
We met that as the vortex core size, right? And there it's physically set by some competition between the gradient term and the alpha term.
Exactly. Yeah, it's done by competing between this term here and that term there.
At some point, I think you called it the coherence length or something like that, or?
Yes. So it is also, yeah. Well, yeah, in BCS theory, it's also the Cooper pair size. Obviously.
Gotcha. Is there an easy way to see that it is Cooper pair size, or, and then also relatedly, what exactly is being coherent over that length?
Yeah, this is just a historical terminology. I agree. There's nothing. The coherence in a superconductor is really infinite because there's long-range phase coherence. Gotcha. So maybe, yeah, let's just interpret C as the Cooper pair or something rather than coherence. Gotcha. Yeah, people call it the coherence length, so that's why I use the terminology, but I agree with you. It's not terribly appropriate.
Gotcha. And then how do we know that it is the Cooper pair size?
Well, you have to start with, actually do a calculation. You start with the BCS theory and you compute gamma and alpha.
I see.
And then you look at square root of alpha or gamma, you'll find it's basically the Cooper pair size.
Gotcha. But is there an obvious reason why it should be the same thing as the vortex size?
No, it isn't in general, but it is for a weak coupling BCS superconductor.
I see. Okay. Gotcha.
Yeah.
Thank you.
Sure.
I have a question.
Yeah.
So if we were to suddenly,
I've been pointing to the text and not knowing I haven't shared the screen. Sorry. Okay. Sorry. Yeah. Go ahead. Yeah, Maine.
So if we were to suddenly turn off the B field in that example, I guess I'd expect that like the vortex configurations would be like unfavorable without the B field.
Yeah.
And so if they were to dissipate, would we like expect like, I guess like the energy from them would like gradually like go down, or is there like some kind of like discrete like unwinding of them that has to happen?
Oh, that's a good question. I mean,
I don't know
because
if that makes sense.
it's hard for them to unwind because they're all vortices. It's not a lattice of vortices and anti-vortices. They all have the same circulation, which is set by the Bx. If you turn the B field on, well, I don't know. They'd probably just radiate some electromagnetic waves and lose the energy that way eventually, or the sample would heat up, and therefore psi will become normal, something like that. But if you just turn the B field off, yeah, I'm not sure. I think it'll just radiate the energy away. Yeah, you probably get some electromagnetic radiation coming out very quickly. Yeah, that would be my guess. But it's a good question. I may be guessing here. Yeah, I am guessing.
Okay, thank you.
Yeah, sure. Yeah, there'd probably be some microwave radiation or something, and the vortices would disappear. Maybe some local heating also. Yeah.
Can I ask, they would be like quantized until they like went to 0 or something, or until they radiated away, like the circuit, if you know what I mean?
Well, I mean, I think quantization is energy. Once you're talking about a highly non-equilibrium situation now, and energy may not be even a relevant quantity. So I don't know. I think the quantization you'd lose right away, because minimizing energy is only something you want to do in equilibrium, and now you're in a highly non-equilibrium situation. I don't see any reason why the flux would be quantized there.
Okay, thanks.
Sure. Okay, well, great questions. All right, that's the end of this chapter. So let's now start the next chapter, which is formally the Bose-Hubbard model. But before I do that and put up the notes, let me go back to the board and just introduce what we've done so far. What time is it, by the way? Oh, 10 minutes or so. Okay. So basically what we've done so far is look at phases that are smoothly connected to the weak interaction limit. So we've studied basically weak interactions for both fermions and bosons. So what happens for a weakly interacting Bose gas is that goes superfluid. What happens for a weakly interacting Fermi gas? Well, it's mostly a Fermi liquid, but at very low, exponentially low temperatures, it can become a superconductor. Now, it may well be that in certain systems, these phases that we now understand fairly well persist all the way out to strong coupling. So then you can get what's sometimes called a heavy Fermi liquid, where the quasi-particles are strongly renormalized, but they're still there. Or strongly interacting Bose gas like helium-4, which is not in the weak interaction limit, but is basically the same adiabatic, same superfluid that we have learned, except the numbers are harder to calculate. So the question is, that we're going to answer in basically the rest of the course. What are the new phases? Our new phases at strong interaction. Is there something really different? Okay, and the answer is there is something really different that appears even in the electron gas or even in helium at strong enough interaction, and we actually know what it is. So, and that's in the case of the electron liquid, we call it the Wigner crystal, and for helium-4, we just call it a solid. It just becomes a crystal. So electrons at strong interactions, which if you actually think about it and and look at the interaction energy relative to the Fermi energy, that those are electrons at low density. curiously, for the electron gas, the low density regime is where, because at low density, the Fermi energy becomes very low. And at high density, the Fermi energy is so high, it's much larger than any Coulomb interaction. So at low densities or strong interactions, what electrons like to do in 2 dimensions anyway, they form a triangle lattice. So this is called the Wigner crystal. So this is the Wigner crystal. And what this means is that each electron is some, say, a Gaussian wave packet sitting here. And then they're localized in fixed regions, and it just sits there. And then what are the excitations? Well, okay. There are no quasi-particles in the sense of fermions. These electrons can't move. They're basically stuck in this crystalline arrangement. So the excitations here are actually just the vibrations of the crystal, the phonons. So in the crystal, the excitations are just phonons. Now, because of the long-range Coulomb interaction, the compressional mode maybe have a higher frequency, like the plasma frequency, but they're shear modes, which are just like ordinary phonons in a Wigner crystal. So they're basically Bose excitations, some kind of phonons. And this is a pretty well understood problem. It's just harmonic oscillators really at the end. You can ask, how does this thing conduct electricity? Well, if you applied an electric field, certainly the whole Wigner crystal can slide. So you would think it's a conducting medium. But in a real sample, there'll always be some impurities. You'll have some impurities, and the impurities will pin the crystal. So it'll just get stuck and you won't be able to move it. So it's really an insulator because of pinning from weak impurities. It's very different from a Fermi liquid, which has no problem conducting electricity, even in the presence of impurities. The electron just scatter off them because they're in plane wave states. In Wigner crystal, the whole crystal gets pinned. So it's an insulator, and it has only Bose excitation and low energies. And that's all there is to it. It's really something you can understand from a semi-classical theory. Okay, so we want to basically study these insulators a bit more. Also, you notice that if you did this theory for helium-4 forms a solid, it doesn't have Coulomb interactions, a solid at high pressure for different reasons. But then, as far as the theory of helium of a boson crystal or an electron crystal, the theory is not very different. It's only some very high order processes where you even know that these are fermions. You need to have some exchange processes where the electrons go around a ring before the fact that they're fermions makes any difference. But those processes are extremely rare at low temperatures. So the theory of a Bose crystal or a fermion crystal is not very different for most purposes. All right. Now, so we're going to study this crystal a bit more, but really we want to understand something about what's called the metal insulator transition. So what happens, for example, for electrons where I start slowly increasing the density? Then at some critical density, suddenly it must have a phase change from an insulator to a metal to become a Fermi liquid. When does that happen? Well, we don't know fully well the answer to that question even today. So that's a difficult question. But what seems to be pretty sure is that transition is a first order phase transition. That suddenly it jumps from this crystal to a metal. Yeah, so it's not a quantum phase transition that's very easy to study because several things are happening near it. One is that the crystal is melting, so the broken translational symmetry in a crystal is disappearing, but you're also getting the Fermi surface appearing. That's very complicated. So we're going to study a simpler problem where we're going to study the analog of a crystal, but in a configuration where the crystal actually doesn't break any symmetry. And there's an insulating phase that doesn't break any symmetry. And then there's a superfluid phase. So this will be for bosons. Okay. And this is just turns out to be a problem which, you know, when it was first looked at was just ideal speculation, but now with optical lattices and ultra cold atoms, there's no problem actually realizing this and studying this in great detail. And it's one of the best examples of a quantum phase transitions that we're going to now look at. So now we imagine the following model. So imagine you have a fixed lattice. These are some potential wells. So this is V of X. I'm only drawing one side of it. And there's some bosons. And they want to sit, they one state. So some site can have two bosons, other sites, and there's some, empty, maybe one boson over there. So what are the things that can, and so this is some lattice, usually it's an optical lattice, and there's some bosons moving in it. And when both of them sit on, there's only one state on each side in terms of an orbital. There's some, there's some wave function for this boson sitting on this side, and we forget about all the other states. They're either not bound or they're much higher in energy. So what can happen is that a boson can hop from here to there, that it can tunnel from there to there. That gives you some matrix element T. Well, usually you make that negative, so minus T. And then anytime you have two bosons on a given site, they cost you energy U. All right. So what do you expect in different limits? So now for weak interaction, so U is, this is the energy for putting two bosons on each side. For U much, much smaller than T, what you should get is a superfluid. And it's just very weak interaction, or BEC. Not in free space, but with some dispersion in the lattice, the hopping from this hopping matrix element T, EK, which will be something like minus 2D cosine K or something like that in 1D. So there's some dispersion, is not K squared, it's some periodic function of K. And since U is small, you can just take the lowest energy state and put all your bosons in it. And then you do the Bogoliubov theory. Everything just goes through with the new value of EK. It's really no different from the theory we've already done. However, we can imagine a different phase in the U much, much greater than T limit. And this is the simplest example of an insulator. We call that an insulator, thinking these are charged bosons, sometimes also called a Mott insulator. The word Mott is usually used when you're getting an insulator that doesn't break any symmetry, whereas if you do break a symmetry, that could be a Wigner crystal or a charge density wave and many other complicated things. So what happens in U is much, much bigger than T. Well, then you have, a particular state where you have one boson per site, for example. And this has a very low energy because the bosons never pay the energy cost U. But anytime, and if you now want to move a boson, if you move it from here to there, suddenly you have to pay cost U, which is practically infinite, so it won't ever go there. So basically the boson will be stuck because of the repulsion, and this is anything but a superfluid. So now our next task is to understand how you go from here to there. We want to, for this simple model, you can actually compute this very well. You can do it on a computer and you can test it with experiments. Everything works very beautifully. And so this turns out to be the very simplest example of a phase transition from a weak coupling phase to a strong coupling phase that we can study. So that's what we're going to do.
Sorry, does the sign of this interaction matter?
Absolutely, it has to be repulsive. Thank you. Yeah, if it's attractive, well, then all the boson will just sit on one site, and you get it'd be an instability. You just put everything on the same site. That's also true for the free Bose gas. I mean, for the Bose gas in the continuum, without a lattice, it just if it's attractive, it's just totally unstable.
Right, but for fermions, it wouldn't be unstable, right?
Fermions is more complicated. Yes, so we're not talking about fermions. Fermions, you have to also worry about the spin in any real situation. And metal insulated transition for fermions are much more complicated. Maybe we'll say something about that towards the end of the course. I mean, even to get a superfluid, is more, you need pairing, and so yeah, fermions. So we'll just talk about bosons for now. As and I don't have to even get bosons because in the last 20 years, this has become a routine thing that people study in the laboratory now. It certainly wasn't when in the 80s when people started studying these things. Nobody imagined that someday it'll be so easy to make these Bose-Hubbard models. Other questions?
I have a question.
Yeah.
For this second option, if we were to have one of the bosons be missing, if it wasn't completely filled, wouldn't that hole conduct quite easily?
Yes, thank you for pointing that. I should have mentioned that. Yes. So there is a new condition here for these type of insulators, which I didn't have for the Wegener crystal. The number of bosons, that's very important, must equal the number of sites. So that is exactly one boson per site. And if you think about it a little bit, it can be any multiple of the number of sites, an integer multiple. So the insulators only form at what are called commensurate densities, 1 per site, 2 per site, 3 per site, and so on. And the reason is exactly what you said. If you had even one boson missing, or one extra boson, either way. So this, you have these bosons sitting, but there's one hole. Okay, and now this can move here with then no energy cost because the hole would just move there. And so this hole would move around, and you'll have maybe some density of holes far enough away. So at low enough temperatures, you're going to get a superfluid. This hole will Bose condense. You get a superfluid of holes. And just if you're missing one atom, if you add an atom, suppose you had 2 atoms here, well, this thing on the top can move freely, just like as if the other atoms weren't even there, because its energy is the same on every side. And so this extra atom will go superfluid. But now you see another very interesting thing. I said without proof that in the continuum, the superfluid density is the total density of bosons. That's simply not true here. If you just had a few extra bosons, the superfluid density you would think is related to the extra bosons. These things will not contribute. And yes, that's what you find. And we'll now show how you do a calculation that can account for all of that. Right, so mod insulators only occur at commensurate densities. Now you might think, okay, this is useless. How can you precisely choose the number of density bosons to equal the number of sites? Well, often the system does that on its own. It's connected to some reservoir. It'll always, if it has some extra bosons, it'll, under the right condition, it'll pay for it to get rid of them and chuck them outside. This will find the right density to make it. Okay. Further questions? All right. Well, then that's the end of the lecture. Then there'll be a review session as usual tomorrow morning, and I'll also website, and also let me just show that before there's notes on the boson follow. Hello, are you still there? Okay, can you hear me? Somebody
Yes.
say something. Okay, great. So I was just sharing. Sorry, my connection died for a minute. Yeah, so these are there are notes here on the Bose-Hubbard model from my book. I've extracted, and we're going to just go through these notes next time. Yeah, so here's the model that I've been qualitatively describing so far. Okay, so see you soon.
Thank you.
Thank you.
Thanks.
Thank you.